Okay, this is the derivation of the big kinetic theory equation. It's got to be derived by first principles, but it's pretty easy to derive. It's just that there's quite a few steps. So we start off by considering a single particle, mass m, contained inside a box, a cubic box with sides L. Okay, every side is L, it's a cube. We've got two sides labelled 1 and 2. The particle travels with speed c in the x direction, hence cx. Its mass is m, it's moving with velocity cx, so therefore its momentum is mcx. At phase 1 it collides and momentum is reversed, it's an elastic collision. The momentum is now minus mcx. The momentum change is the initial momentum, take away the final momentum, which gives us 2 mcx. So after the collision, the molecule travels distance 2L before colliding again with phase 1. This takes the following time, t is equal to 2L over cx, and that's just time is distance over speed. Now you'll be pleased to see that my handwriting's a little bit better on this slide. Magic. Right, so taking what we had from before, we're going to develop it just a little bit further. We had time and force. Now if we look at impulse, we had time and we had momentum. Now impulse is just change in momentum. So if we use impulse is force times time, we can rearrange and get the force is the change in the momentum divided by the change in time. And both of those were calculated on the last slide. So we have 2 mcx for the change in momentum, and the change in time is 2L over cx. So dividing those through, the cx, because when you divide by a fraction you multiply by the reciprocal, the cx terms become a squared, the 2's cancel and you're left with an m and an L. And that gives us a force. A pressure is force over area, so we now have the force, and because the area is L squared, because it was a cube and all of the sides were L, we're left with this. Now we can combine the L's, they're all divides, so we end up with this L to the power 3 mcx. Remember, c is the speed of the particle. Okay. Now for n molecules we have p is equal to m L to the power 3 and then a sum of all of the molecules. Now if they're all travelling at the same speed, we can just multiply that by a factor of n. The factor of n just comes from the fact that there are n molecules, and this L cubed term can be simplified just a little bit to give us a volume. Now there's a little bit of statistics coming up here. Because all of the particles are travelling at the same speed, I'm going to use C bar. Now there's a very good reason for using C bar, and that's because I have awful handwriting and nobody can tell. Now if I write it bracket C, that just means average speed, but so does C bar. Now, so as nobody's getting confused by me thinking I'm writing 2 C's and then a closed bracket, I'm going to keep on writing C bar. So to carry on with the statistics, I'm not going to be using C in brackets, I'll be using C bar. Now if we look at the total speed, okay, the total speed is combined from the 3-dimensional components. But for a large enough number of molecules, on average they'll be the same. So you can just put it as c squared. it's just Pythagoras' rule here. And then we look at the average, we've got cx squared, cy squared, cz squared, all in averages. So for a large number, cx, cy and cz are all equal, and then you can take that and you can say that c squared, or c bar squared, is equal to 3 cx squared. So that's then rearrangeable to give you c bar x squared is equal to 1/3 c squared. Confusing, but the maths follows. So the pressure follows this rule, and then we get PV is 1/3 nmc squared. And here I've reverted to the average sign just to show it as it's shown in the CIE specification. So this is a little bit of an extension, and it takes PV equals nRT, and PV is 1/3 nmc squared, and equates them to give you nRT is 1/3 nmc squared. Now, kinetic energy is half mv squared, or you can use C rather than V, as we have done so far. So equating them, we have this. Half mc squared then becomes this. N is the number of moles, N is the number of molecules, but the number of molecules divided by the number of moles is the same as Avogadro's number. So this slightly complicated formula becomes this. But R divided by NA is a different constant K. Okay, so the kinetic energy is equal to 3/2 kT, and that's a little extension linking kinetic energy being equal to the temperature, or proportional to the temperature of the molecules. And there we go. Hope you've enjoyed. If you have any issues, watch the video over again and see if you follow. Okay.